Alright, in this video, we study what's common among the following sets: rational numbers, real numbers, and complex numbers. On these sets, we can apply addition, subtraction, multiplication, and division in the same manner. And this common behavior can be summarized in the notion of fields. So these three sets are examples of the field. So we will give the axioms and some simple common properties of these fields. Okay, let's start. Okay, first let's start from the definition. Let F be a set which is equipped with two operations called addition and multiplication. Okay, and these operations satisfy the following axioms. That is, 1. F is closed under addition. Under addition. That is plus operation. So this plus and multiplication, they are binary operators. Okay, meaning it operates on two elements of this set F. So what it means, so closed, what closed means is the following. For any element A, B of this set F, if we add them, so if we apply this operation on these two elements, then the result is still within the same set F. So in this sense, F, the set F is closed under addition. Okay, and second, this addition operation is commutative. I hope by now you are familiar with this term commutative. So that means for any elements A and B of F, we have A plus B is equal to B plus A. So we can swap the order of operation, addition. And we already know this is very, this applies to all of these sets, right? And 3. Associative. So for any elements A, B, C of F, we have associativity. That is A plus B plus C is equal to A plus B plus C. So that means how we add elements doesn't matter. Okay, it always gives the same result, irrespective of the order of addition. And fourth, there is a special element called 0, such that for any element in F, we have A plus 0 is equal to A. So this is called additive identity element. Okay, note that this symbol 0 is just a symbol. Okay, it's not necessarily the number 0, but it's just a symbol to represent some special element of F that satisfies this property. Okay, additive identity is also called the 0 element often. And next is the existence of the additive inverse for each element. So for each element A in F, there exists some element in F such that A plus B is equal to 0. So this 0 is this 0, okay? Additive identity of F Okay, so such B is called additive inverse of A, and it's denoted by negative A. Okay, so in this sense, this B should be actually can be written as negative A, and A plus negative A is equal to 0. So we can always find additive inverse for any element in F, okay, if F is a field. So far, we introduced 5 axioms concerned with addition. First was closure condition, closure. And the second is commutativity. And the third one is associativity. And the fourth one is the existence of identity, additive identity. And the fifth one is the existence of additive inverse. Okay. Next, we introduce 5 axioms that concern with multiplication. Okay, so 6, F is closed under multiplication. So let's see. So multiplication we denote by star. Okay. So that means for any element AB of F, A times B is still an element of F. So it doesn't go beyond this set, okay, as a result of multiplication. And 7, this multiplication is commutative. So that means for any elements A and B in F, we have A times B equal to B times A. So we can swap the order. And 8th, multiplication is associative. So that means for any elements A, B, C in F, we have A times B times C. So first we multiply B and C and then multiply by A. This is equal to A times B times C. So that is, we first multiply A and B and then multiply C, and the result is the same. And of course, because of this, we can just write, without parentheses, we can just write A times B times C. By the way, same is also true for addition, so we can just write A plus B plus C instead of this or this. Okay, so the next is the existence of multiplicative identity. So there exists a special element. We usually call it 1. So this 1 is not number, okay, in general. This is just a symbol that represents a special element of F such that for any element of F, A times 1 is equal to A. So multiplication by the multiplicative identity doesn't change the element. Okay. And 10, the existence of multiplicative inverse. But we need to pay a special attention to this. That is, for any element A of F, if A is not 0, so this 0 is not number 0 in general, but it's the additive identity, okay, which we introduced in the axiom 4. Except A, then there exists some element in F such that A times B is equal to 1. So this one is this one, okay, it's multiplicative identity, not number 1 in general. So this such an element B is called multiplicative inverse. Okay, and we usually write it as A to the power of -1. So A inverse. Okay, so let's write it like this. So so for each element A, as long as it's non-zero, then there is its multiplicative inverse called A inverse, such that A times A inverse is equal to 1. 1 is multiplicative identity. Okay, now we have 5 axioms that concern with multiplication, and then finally 11 we relate multiplication and addition. Okay, it's called distributive law. So that is for any element A, B, C of F, we have the following equality. A times B plus C. So this means first we add B and C and then multiply A to the result of that addition. This is equal to A times B plus A times C. So we can distribute multiplication over addition. Okay, so that's all the axioms that define a field. So any set with addition and multiplication, those are binary operations, if these 11 axioms are satisfied, then the set F is called a field. Okay, field. So usually, so field is a set, but not just a set, but it comes with two operations, two binary operations, addition and multiplication. So sometimes we call this triple, so F plus and star multiplication. This triple is called a field. But unless otherwise stated, we just say F is a field, so set is a field. So that implicitly says that there are two operations, this and this, that satisfy these axioms. So let's see some examples. As we have stated as an introduction to this video, the set of rational number is a field, and the set of real number is a field, and the set of complex numbers, so they are all fields. Okay. For example, if A and B are rational numbers, A plus B is also a rational number, right? It cannot be irrational. So that means Q, the set of rational numbers, is closed under addition. And commutativity, associativity, and the existence of zero, and the existence of additive inverse, they are all obvious, right? So we didn't define subtraction, but subtraction, like A minus B, is just a shorthand notation for A plus negative B. And negative B is the additive inverse of B, right? So all we need is just addition and existence of additive inverse. So we don't need to define subtraction as a special operation. All we need is just addition. Okay. And similarly, A times B. So by the way, multiplication is written in many different ways. So sometimes we use dot, sometimes we use star, sometimes we use cross. Okay. And sometimes we just write like AB without any symbol in between. Okay. So anyway, so if A and B are rational numbers, then AB is also rational, right? It cannot be irrational. Therefore, the set of rational numbers is closed under multiplication. And also, we didn't define division like A divided by B. But this is just a shorthand notice notation for A times 1 over B, but 1 over B is A times B inverse, right? So B inverse is, of course, the reciprocal of B, which is the multiplicative inverse of B. So B times B inverse is 1, and this one is the multiplicative identity of rational number. So in this way, we can see that the set of rational numbers is indeed a field. And the same argument applies to real numbers and complex numbers. You should try to validate it. Next, let's show some counterexamples. For example, the set of natural numbers is not a field. Because there is no additive identity. Because of no additive identity. Okay, what about n0? That is, so if we add 0 to the set of natural numbers, is this a field? No, it's not. Because here we don't have additive inverses. No additive inverses for any elements except for 0. And also we don't have multiplicative inverses either. So this cannot be a field. What about the set of integers? Is this a field? It's not a field. Why? We do have, so this satisfies all of the axioms for addition. So this, and this, they are satisfied, but and also this one is satisfied, and commutativity is satisfied, associativity is satisfied. However, and also existence of multiplicative identity is satisfied. However, this one, the existence of multiplicative inverse is not satisfied for the set of integers. For example, 2 is an integer. However, there is no multiplicative inverse in the set of integers. The multiplicative inverse of 2 is, of course, 1 over 2, but it's not an integer. So it's not a field. Another example. Perhaps you may be wondering, why do we need closure conditions? So like if A and B are elements of F, why do we need to check this? Or A times B is in F. This seems so obvious, right? But sometimes it's not. For example, if we consider a finite set, let's say A is equal to 1, 2, 3, with usual addition and multiplication between numbers, then this set A is not closed under addition or multiplication because 2 plus 3 is 5. But it's not in A. So A is not closed under addition, and 2 times 3 is 6, which is not in A. So it's not closed under multiplication either. So this cannot be a field with usual addition or multiplication of numbers. So why do we bother to define the notion of field anyway? One reason is that we can see what's the universal property among different kinds of things. So by using the notion of field, if we can prove something is true for any field, then we don't have to prove the same thing for different fields. Like if we can prove for general field F, and we know that rational numbers, real numbers, and complex numbers are all fields, so we don't have to prove the same thing for each of them. We can just prove only once. Okay, here's one example of such a property. So here's a theorem. Let F be a field. Okay, so this implicitly assumes there is addition and multiplication. Okay, so they are defined somehow, and they all satisfy the axioms of the field. Okay, then first, for all elements f of f, f times 0. Of course, 0 is the additive identity. Then the result is 0. Okay. Recall that we did not specify this condition as a part of the axioms. This is actually a derived property from the axioms. And 2, for all elements h and k of the field f, if hk, so h times k, is 0, so the multiplication between h and k is equal to the 0 element, then either h is 0 or k is 0. Okay? If you know, of course you know, arithmetic of ordinary numbers, like real numbers, these properties are so trivial. But these properties are not specific to numbers. As long as a set is a field, the same thing happens. So it's a universal property among all fields. So let's try to prove this. First, so f times 0 is equal to f times 0 plus 0. So this is because of the property of additive identity. Because additive identity. Remember, for any element, if we add 0, then the result is that element again. So this a can be 0 also. That's what we used here. Okay, so 0 plus 0 is equal to 0. That's why we have this. Okay, now, using the distributive law, this is equal to f times 0 plus f times 0. So distributive law. Now, to both sides, add the additive inverse of f times 0. So we have f times 0 plus negative f times 0. Of course, f times 0 is an element of f because of the closure condition. So negative f times 0 is also an element of the field. So if we do that, we have negative f times 0. And since this is, this is the additive inverse of this, so the result is 0 on the left-hand side. And here, this is cancelled by this, so the result on the right-hand side is f times 0 is 0. And we are done for the first part. And for the second part, so suppose h times k is 0, okay? Then we want to prove either h or k is equal to 0. So if h is equal to 0, then we are done. Nothing to prove. Okay, now, so suppose h is non-zero, okay? Because when the case where h is 0 is already handled, so suppose h is non-zero. Then its inverse, multiplicative inverse exists because it's non-zero. So to this equation, multiply H inverse from both sides. Then we have H inverse HK equals to H inverse times 0. Okay, and from the first part, the right-hand side here is 0. Okay, and the left-hand side, by associativity, we have H inverse times H times K, right? And by commutativity, we have H times H inverse on the right-hand side. Okay, and this is equal to 1 by the definition of multiplicative inverse. And 1 times K is K. So K is equal to 0. So if H is not equal to 0, then K must be equal to 0. Therefore, we are done. So either H is 0 or K is 0, and we are done. So these properties are universal properties of any fields. So far, we know these fields, Q, R, C, but there are also other fields which we may encounter in future videos. And so that's all for this video. See you later.